All right, AP Environmental Science, the living world and ecosystems, global currents and biomes. This video will be on air currents. By the end of this section video, you should be able to explain how the properties of air currents affect the way the atmosphere moves, identify some factors that drive atmospheric conditions and convection currents, describe how Earth's rotation is affected by air currents, and then explain how the movement of air currents over mountain ranges also affects climates. The atmospheric convection currents cause air to move directly north and south. However, the actual air currents on Earth's surface are deflected to the east and west because the planet is rotating. So it's this rotation of Earth that causes the deflection of objects that are moving directly north or south. And this is a phenomenon that we call the Coriolis Effect. As Earth is rotating, its surface moves much faster at the equator than it does in mid-latitude in like the northern and southern pole regions. And it's this faster rotation speeds that are found really close to the equator that causes objects that are moving directly north and south to deflect. This deflection that is due to the rotation of Earth is specifically what we call the Coriolis Effect. And so prevailing winds of the world are produced by a combination of those atmospheric convection currents and the Coriolis effect. So if it wasn't already complicated, now we're going to add Earth's rotation to the equation. All right, looking at this diagram here on the left-hand side, imagine that you can stand directly at the North Pole. If you throw a ball directly south, like all the way down to the equator, if Earth did not rotate, the ball would travel directly south to the equator in a straight line. But because Earth rotates to the east, while the ball is traveling, the ball will land in a location that is west of its intended target. And this happens because Earth's surface beneath the ball is moving faster than the ball towards the equator. In other words, the path of the ball is deflected with respect to the given location on the globe. All right, so now imagine that this is at 30 degrees north and 30 degrees south latitude. So you're standing somewhere on the Florida-Georgia border, Mexican-American border. All right, that's where you're standing. And now you throw a ball. You're going to throw it again towards the equator. So if the air current started there, like on the border of Mexico and the United States, and you throw the ball, then you get this deflection outward. Now, if you're standing at that same border, you turn around, and now you're going to throw it towards the North Pole. Its deflection will be in the opposite direction. And this has to do with both reasons, both the currents and the rotation of the Earth. So let's see if perhaps we can bring some of this together. All right, the deflection of an object moving north or south occurs because the planet's surface moves much faster at the equator than it does at higher latitudes. So the planet's circumference is about 40,000 kilometers. That's 25,000 miles, I don't remember the exact number, at the equator. And it decreases to about 7,000 kilometers or 4,300 miles at 80 degrees north and 80 degrees south latitude. All right, so now imagine traveling all the way around Earth in 24 hours. Now at the equator, you're going to travel 40,000 kilometers, whereas at 80 degree north latitude, you're going to travel only 7,000 kilometers. To make the trips in 24 hours, you must travel much faster at the equator. So indeed, Earth's surface moves at 1,600 kilometers per hour. That's a little over 1,000 miles per hour. At the equator, however you want to say it, but it's only 291 kilometers, 181 miles per hour at like 80 degrees north or 80 degrees south latitude. So if the Earth did not rotate, the air and the convection cells that we discussed earlier would simply move directly north and then south and then back again. Prevailing winds have a pattern around the world that is produced by a combination of both these atmospheric convection currents and the Coriolis effect. Alright, so because Earth's speed of rotation is faster near the equator, the path of the air currents moving towards the equator is deflected west, just as we saw in the throwing ball example that I did earlier. This deflection causes those Hadley cells north of the equator to produce prevailing winds along Earth's surface. We call those the northeast trade winds. Sometimes you hear about that on the news. Whereas the cell that's just south of the equator produces prevailing winds that come from the southeast, and we call that the southeast trade winds. So this Coriolis effect also explains the prevailing wind directions that happen between 30 degrees and 60 degrees latitude, and we know those as the Ferrel cells. So these winds can be quite variable. There's a lot of mixing air currents there, and they're also adjacent to the other types of cells, the Hadley and the polar cells. And so if you look at this diagram, because Earth is rotating faster at 30 degrees than it is at 60 degrees latitude, this air movement toward the poles is deflected east in the opposite direction there. And so as a result, the prevailing winds that are above 30 degrees north are coming from the southwest, while the southern hemisphere, those prevailing winds above 30 degrees are coming from the northwest. So, but in both cases, those winds are called what we call the westerlies. So finally, this Coriolis effect helps us understand the prevailing winds and the direction of the currents in the polar regions. So along with Earth's surface, the polar cells move air between the poles and then towards 60 degrees latitude. Since Earth is rotating faster there, like at 60 degrees latitude, than it is at the 90 degree latitude mark, then this air is deflected to the west. And then the polar winds come out of the northeast in the northern hemisphere, and they come out of the southeast in the southern hemisphere. And that's how they get the name easterlies. All right. A rain shadow is a region where there's very dry conditions that are found on leeward side of mountain ranges. And as a result, these humid winds that come from the ocean cause a lot of precipitation on the windward side. So essentially, a rain shadow works like air moving inland from the ocean contains a large amount of water vapor, right? It's coming off the ocean. So when it meets the windward side of the mountain range, the side that it's facing, it starts to rise, and it goes through that, it starts to experience that cooling process. But water vapor condenses as it cools, right? So then clouds form and then precipitation falls. The presence of the mountain range that is there just causes this large amount of precipitation to fall. And so when it falls, the cold air that's dry, it travels to the other side of the mountain, which is what we call the leeward side, where it descends and experiences this high pressure, and that is a heating condition. So the air is now warm and dry, and it makes these really arid conditions on the other side of the mountain. So rain shadows occur, where right off of an ocean where the wind is blowing inland from the ocean and it meets a mountain range. The side that faces the wind coming in is what we call the wind facing or the windward side. And basically it hits the mountains, air rises and cools, and large mountains form a lot of water vapor, so clouds form at the top of those mountains, and then they experience a lot of high precipitation. And then it makes it over the other side of the mountain, what we call the leeward side of the mountain, where air starts to cool. It becomes very dry. It's lost all of its moisture, and it descends descends on the other side of the mountain, causing these really, really dry, heated conditions that are warmer and drier than the air coming off the ocean. All right, I know that's a lot, so thank you for Joining me here, ocean currents is next.